Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
We start. It's a real pleasure today for me to be introducing Sihem Amiryaya from AT&T Labs. I keep wanting to say Bell Labs, but I know that's wrong. Sihem received her PhD from INRIA, actually from University of Paris, although she tells me that her total interaction at University of Paris was to early in the degree program to go in and sign up, and at the end of the degree program to show up and hand in a thesis. And all the work in between was done at the INRIA Research Lab with Claude Delobel and Sophie Clouet on bulk loading, data bulk loading. Since then, she's been at AT&T working in Devesh Srivastaba's group and collaborating with many members of that group who I'm sure many of you know, like Mary Fernandez, Nick Kudos, who's now back at University of Toronto, and others, and virtually all of it on XML-related technology, and has become a real leader, particularly in the area of text and information retrieval technology as it relates to XML database processing, which is what she's going to be talking to us about today. And fire away.
Thanks, Phil. Hi, everyone. So, as Phil said, I'm going to talk about XML full-text search and scoring. The talk is organized in two parts. The first one is going to be about extensions to XQuery and XPath to handle full-text search. And I realize it's a bit too long, so I'm going to try and be as quick as possible about the first part. And the second one is about scoring, which is still very, I would say, recent, immature, going on. Okay. And the second part is going to be more about some general directions and what we've been doing in the past 3 or 4 years. So let me start. So the motivation comes from the fact that XML is really able to represent a mix of both structured and unstructured data, even if the focus has been mostly on structured data, especially in designing XQuery and XPath languages. So example of repositories that contain such a mix of structured and unstructured data are the IEEE INEX data collection, and this is a set of documents that are being put together by mostly information retrieval people in the past 3 years to do assessments of systems and scoring systems for XML. It's very much like track for just ASCII data and HTML. And here they've been putting together data to sort of say this is a reference data collection over which different systems are run and then compared, and the ranking methods are compared based on the results, user assessments. The second second data collection I want to mention is the Library of Congress collection, and the US Library of Congress has been sort of turning their data into XML in the past 2 years, and it's great because it's accessible and it's real data, and it has really a lot of text interleaved with structured data. Anyway, so these are the two major data collections that we've been looking at, and there are obviously others. And the first whatever criticism or thing from which we started is that existing XPath and XQuery languages are really very good at navigating in the structure of XML documents. They can go pretty much in all directions, but they're quite limited in querying text, and by querying text I mean full-text search. So there are these two main activities which don't really talk to each other, and we're trying to make them talk to each other. One is the W3C one, which started with XPath XQuery and now is going towards XPath XQuery and full-text, and the INEX, which is the one that's more geared towards doing assessments of existing systems to do ranking, basically. So the outline of my talk is going to be this first part, which is about motivating and understanding the extensions to XPath and XQuery to handle full-text search. And the second one, which is going to talk more about scoring, and then I'll finish with some open issues. The first part is organized as follows. I'll first go through what full-text search is, examples, and then sort of a definition of what we want full-text search is. Then I'll describe TeXQuery, which is the first language that we came up with, which extends XPath and XQuery with full-text search capabilities. And then XQuery Full-Text, which is the language that the W3C is working on, which is mainly based on TeXQuery. So I'll go through the syntax, data model, and semantics. And then I'll describe our implementation, conformant implementation of XQuery Full-Text, which is Galatex. And this is all joint work with Chavdar Botev and Jay Sharmugasundaram from Cornell, with whom I worked on TeXQuery, and Emiran Kurtmola, who was doing an internship at AT&T and who helped me implement Galatex. All right, so here's what we mean by full-text search queries. This is a piece of text that is embedded within structured data, so it's an XML document. Obviously, it's a very simple one, but you look at the Library of Congress documents, they're sort of all like interleaving text and structure, and they're much larger. So the kind of queries that we're interested in are queries that want to, for example, return book paragraphs containing the keyword software and stamped forms of usability and not containing the keyword rows. Okay, so obviously, I mean, if you look at just the keyword containment, it's already something that's supported by XPath and XQuery. I'm going to show you examples of how to express that. But we also want things like returning elements containing usability and software or goals within 12 words of each other. Okay, so here already we have what? We have keyword search, we have Boolean between keywords, ands and ors, which is still something that is expressible in XPath and XQuery, but we also have things like word distance, right, which are based on really the positions of individual keywords in the text. And what we also have, as opposed to like major search engines, is the ability to search fragments of documents and return fragments of documents, right? As opposed to just searching the whole document or whatever, or any combination that is just based on searching the whole document and returning only fragments, or searching fragments of documents and returning the whole document. Here we have the flexibility of sort of XML, okay, which is given to us. Which is searching just pieces of documents and returning other pieces or the same. And in all these cases, we may want to, and actually most of the time, we want to return ranked results, right, because we're doing full-text search. So in fact, the full-text search query or search, whatever, can be defined as follows. It has like 4 expressions. Okay, there is a context expression, which means where is the search happening, right? Which is exactly what's happening with XPath and XQuery. You sort of like go in a hierarchy, identify elements that you're looking, identify elements, and then use them as your search context. And I'm going to refer to it as the search context. For example, book chapters. There's a return expression, which is exactly the fragments that you're returning. And in this case, you may want to search over book chapters and return book titles and authors. And in both cases, I mean, you can use XPath and XQuery to do that. I mean, they're very good at that, and we want to leverage their power to sort of identify where to search and what to return. But then the search conditions, we want things like what I showed you earlier, Boolean, proximity, stemming, all operate on keywords, right? So for this, we need new language primitives. And obviously, we also want to be able to score answers based on their relevance to the user query and do things like threshold, top K queries on top of that. Okay, so we need something like a scoring framework, right, to be able to do that. All right, so what were the requirements? I mean, these requirements come from different, have different flavors. I mean, the requirements that are about coming up with a nice language, composable, and, all what we like in the database community, but there are also other flavors that come from the fact that the initial effort was within a standard. So the first thing is obviously we want composable full-text search conditions. So we want to be able to say things like keyword search, proximity, order between keywords is very important. Number of times, for example, a keyword appears. Stemming, stop words, thesaurus, wildcards, apply all this to individual keywords. I mean, there's a long list of this. Okay? What I'm going to present is just a bunch of primitives and tell you why our language is sort of extensible or can be somewhat limited to just a subset of the primitives. So yeah, the initial requirement was to integrate full-text search with XPath and XQuery. And in fact, this is not trivial because XPath and XQuery are based on this notion of nodes, which are elements, atomic types, processing instructions. But when they hit a piece of text, it's sort of just like say, that's it. This is the lowest granularity at which I'm operating. It's at the level of that piece of text. But once you start working with keywords and their proximity especially, you need a finer grained model that sort of understands the position of those keywords and is able to say things like those keywords are within a certain distance of each other, right? And we want all this to be composable. And another requirement is that we want no extension to the XQuery data model. And here there are two reasons. One is purely, I was going to say political, or it's just that nobody in the XQuery group, the standard group, is going to be willing to sort of start modifying the existing data model and redefining the semantics of the primitives that are already there in XQuery to sort of cope with the existing requirements. And the other thing is that if tomorrow you want to query video or other kinds of data, you don't want to go back into XQuery and sort of try to extend it to do that. So we sort of have this notion of coming up with some language that's sort of a co-language that knows how to talk to XQuery and understand what XQuery is telling. And obviously we want to be able to enable answer scoring and ranking. So there are many systems and efforts and papers in this area, and this is really a very informal way of sort of classifying existing systems. The most closely related is SQL which extends SQL with primitives on text, images, and spatial data, and Oracle has like a whole platform to implement SQL And my criticism on this SQL is that first, there is no like clear data model. I don't really know exactly how it functions inside. It sort of is based on this sub-language, which I'll show you an example of. And I mean, it works fine with SQL, but it's not very clear to me how sort of it talks to SQL itself. And you'll see the example. And then there are a bunch of other systems, mainly IR, right, from information retrieval, which do like subsets of what we want to do. Keyword similarity, for example, XXL by Gerhard Wacom and others is just a language that sort of tells you, well, you have a language like XPath, and instead of just having substring matching of individual words, you also have the ability to do wildcards on words, right? So it works for that. XIRQL, which is the main system used, actually it's the language that's implemented in this hierarchy system that's used by INEX as a way of doing assessment, is also very much IR oriented, and it actually has the ability to do relevance ranking. It focuses mostly on relevance ranking. Proximity distance is present in this other language, in query. The other, I guess this is something that we don't have, but it's sort of, these are mostly database languages which say, well, when you start querying text, you don't know the structure of your text, and so you just like put in some keywords, and the system decides for you what fragments to return to you. So it works more. It's more in the perspective of deciding what are the fragments to return to the user. Anyway, the main thing is that, well, there's no support for all of XQuery, and you may not want support for all of XQuery, but at least it's not clear what part of XQuery or XPath is supported in these systems. They provide rudimentary text IR support in the sense that they're very good for certain specific primitives, but there is no way of understanding composability and extensibility of full-text search in those systems. There is no data model, I mean, formal underlying model, and obviously, which means that it's just hard to understand how to optimize across structured and unstructured queries at the level of sort of an algebra and understanding how the two languages. I mean, they're very efficient and they're very good at ranking. It's just that they're algorithms basically.
Had a chance to look at Verity's query language?
No, I didn't look at that. Yeah, no. I mean, I know that it's based on...
They have everything that was there on the previous slide. So,
right.
Except the SQL so...
Right. Right, I know there are things that they don't have, like times, and so thesaurus is just hard-coded in the system.
Right.
It's not something you can express at the level of the language.
Oh.
But I don't know, like, I don't know the system very, very much. What I know also is that the use vector-based scoring.
Right.
So I mean that's just hard-coded in the system too. Okay. So the idea here is sort of have a framework and understand how to plug in different scoring methods, understand how to reduce or extend the language. Right, and yeah, and this is another criticism which I don't solve in this talk, and which we're hopefully aiming to sort of understand better, is that as I said, those systems are very efficient and they're very good at one specific scoring method, but it's not clear what part of the system is doing query processing, like we mean it in databases, which is just finding the set of answers, and what part of the system is doing the scoring. Okay, the one of the main reasons is just that the information retrieval algorithms and programs just function all. Do these two steps all together. They're basically finding elements and scoring them at the same time. And nobody really understands how you can do this in an orthogonal way. And maybe you cannot always do it, anyway. So that's just a general thing. Okay, so just a quick few words about XQuery. It's a functional language and it's compositional. And it's compositional based on this data model, which is very simple. It says, every single expression in the language consumes a sequence of items and returns a sequence of items. And what an item is nodes, like elements and attributes, or processing instructions, comments, and atomic types. Okay, so that's the idea. In fact, the reason I'm mentioning this is also because we want to sort of extend the language in a way that we keep the spirit of consuming sequences of items and returning sequences of items. But it's also because, I'm mentioning this also because it means that you can sort of, like, the first thing you think about when you think of returning elements that are ranked, right, is the ability to sort of return elements and their score, right, results and their score, and carry them around in the language and sort of composing them. And that's not possible, right? You cannot return a sequence of tuples of answers and their scores, okay? It has XPath as a core navigation language, which is great, and which is what we want to use to sort of identify the fragments to be returned and knows that we're searching over. It has variable binding, and the reason I'm mentioning this is that we sort of try to solve this problem of at least at the level of the syntax, the ability to return elements and their scores by using variable binding, which is really which is ugly, but that's what we have so far. And then it has element construction, which allows you to sort of return whatever you want to return, right? I mean, you're searching over chapters, and you're returning titles and abstracts, let's say. So what XQuery gives us is this flower expression, which is very powerful. It's also an expression that consumes a sequence of items and returns a sequence of items. Here the items are books that are identified by //books/book, which is the XPath expression. And what we want to do is to find the books on usability sorted by price. Right? And XQuery does have this fn contains function that does like substring matching, right? So what is really doing this function, it's sort of going into the content, which is either a piece of text by itself, or it computes, it applies a string function to this content, which basically just returns this blob of text, and does some substring matching there, right? And substring matching gives you a certain ability to do, for example, there are other functions like start with and end with, but it really just looks at the whole piece of text as a string, right? And then it allows you to do these kind of things like returning new results and so on, right? So that's one thing. So obviously when you think of doing things like return books containing usability and testing within 5 words of each other, the first thing that comes into mind is to just use functions, right? I mean, XQuery is functional. Why don't we come up with one function per full-text search primitives, right? Which is the first alternative for extending XQuery, right? So contains is able to take a sequence of nodes and return true or false, whether those nodes contain usability or not. Same thing for software. And then you come up with this new function that sort of takes these two and returns this. Obviously, the return type of contains is just not enough to find out about the distance between those individual keywords, right? So that's pretty obvious now at this stage. But we struggled a little bit with this in the beginning, and we're sort of trying to think why these functions are not able to sort of compose completely with each other. But it's just a simple observation. And then the other alternative that we played with a little bit was the SQL MM one, which I was criticizing a few slides ago. And it basically just says, well, instead of just having this substring matching, I mean, just to have this language that sort of is embedded in a string, and that's given to a contains function, right? It's extending the sort of signature and semantics of a contains function to understand more than just a single string and do substring matching. And then you can have a whole, mechanism underneath that sort of goes and parses this thing and does whatever you want. And obviously, this is, the full-text search itself is specified in an interpreted string that is opaque to the rest of the XQuery language. For example, if I want to return book chapters that contain a keyword from their abstract, right? I would need to sort of do all sorts of string concatenation, evaluate the abstract, put it in, and then create my string and give it to the system, right? So I don't have this, at the level of my language or the syntax itself, I don't have the ability to sort of easily parameterize or easily understand what's compose the different primitives. Okay, so that's how we came up with TeXQuery, which has these composable full-text search primitives that we call FT selections. It's composable with XPath and XQuery also, so it's composable within itself and with XPath and XQuery. It's based on this data model, which is called full match, right? And you'll see it's a very simple data model. It's just basically keywords and their positions that we're carrying around. And then it has some ability of scoring and ranking, which is, to be honest, still like completely unclear. And it actually was used as a basis for XQuery Full-Text, okay? So just as a quick, maybe pictorial way of sort of understanding how TeXQuery functions, well, basically what's happening is that TeXQuery is here. It has these full-text selections. It has its own grammar. It has those full-text selections are based on this full match model, and they compose under that model. So they evaluate to a full match and a return full match. What XQuery is able to understand is sequences of items, mostly just sequences of elements. And the way it talks to TeXQuery is by sending those elements over which a search is going to happen. And then this expression is going to say true or false, or just filter those elements that contain or don't contain this expression, don't satisfy this expression, and return them back here, okay? So just a few words about XQuery Full-Text. It's a language that came from this Full-Text task force, which is like a task force from the XQuery working group that started in the fall of 2002 to extend XQuery Full-Text search capabilities. It has all these members and a few more. And there are a few public documents, and public comments are very welcome. So the most important document is the XQuery Full-Text, is the first one, which is basically the language specification document, and it has the semantics and everything. And believe me, it's just easier to read than the XQuery formal semantics document. The first version of these documents came out in July 2004, and the second one in April 2005. And I'm here this week to sort of discuss the next version. This one is nice. I like it because it sort of had just examples. It's just example-driven and mainly from the Library of Congress. It sort of shows the different kind of queries that we wanted to support. And then this one is the one I like the least because it sort of just talks about what we should do and what we should not do. But anyway, just so that you know that these documents exist and that you're welcome to send comments. And there is an email, actually, to which comments can be sent, which is mentioned at the beginning of each document. OK, so let's go into the language. All right, so in fact, the language is, at the level of the grammar, it's very simple. It extends for the search, just for search. Think of it as being just a Boolean search, like we think of it in databases, right? An answer either satisfies or not a query. So we extend XQuery with a new expression, which behaves exactly like other XQuery expressions. It takes in a sequence of items and returns a sequence of items. Right? Here, the context expression is any XQuery expression, which identifies our search context. And then we have this keyword, and then we have all this language, FT selection, which I'll show you through examples in a few minutes. The expression itself, as it's written here, returns true if at least one node in the context expression satisfies FT selection. So it really behaves like XPath, right? I mean, this is like a predicate in XPath, and it returns true or false, depending on whether the node satisfies or not. And then obviously, you could also return nodes if you want to treat, this part as just a predicate that filters elements or identified here. And true is part of the XQuery data model. It's actually a sequence of just one value. And then there is scoring, which you'll see. I'm mentioning it here, and then we'll forget about it for a while, and then I'll come back to it just as a research effort, mostly. Right now, all we have is sort of just like a user-level syntax, which is still under discussion. But it's basically just doing something like binding scores to variable names as, and the score evaluated by some secret source. I'll talk about scores more, later. All right, so here's a language. Look at examples. The language actually supports all sorts of primitives. I mean, this is sort of a very informal grammar, right? It says an FT selection is an FT word, which is basically the terminal. And then it has ands and ors and nots and mild nots and order and window and distance and scope and times. And it also composes with something called FT match option. Let's forget about match options for now. So basically, an FT word is just like this, right? This is how it's used in XPath. It returns this expression, returns titles, basically, that satisfy this, right? That contain usability. Okay? And this is, in fact, equivalent to FN contains for now. This expression returns abstracts that contain usability or web testing. And this is equivalent to an XQuery or between two FN contains between books and abstract. But then once you start having things that are more sophisticated, like window, obviously you cannot express them in XQuery. So what we have here, for example, this one, what's returning is true or false, depending on whether there is at least one book content containing usability and software within 3 words of each other and appearing in this order in the text. Okay, so these are all composable primitives. Ordered is an FT order, which is here, which can appear pretty much everywhere. Okay? And window is an FT distance, which can appear also anywhere, and so on, right? So this one returns a book abstract that contains usability and web, same sentence. So this is FT scope. Okay? So this is a scoping within a sentence. Okay, these are all like primitives that people use in information retrieval. We just sort of turn them into primitives and try to understand how they talk to each other and whether they're atomic or not. And, this is a times. Where is it? Here. Okay. And then this is returning. Oh, okay, so this is funny because what it does is that it returns section titles for those sections that contain at least one word from the book's title. Okay, so you can see that XQuery expressions can be embedded within full text XQuery full text expressions, and this is an FT word, right? That evaluates 2 strings. That's the condition. Okay, so you can and you can see how much anything that basically evaluates to a string here can be used. Okay, within XQuery. So you can call XQuery within XQuery full text and vice versa. Okay.
So in this particular example, usability has to occur before software.
Right. In this one, right? Yeah.
In which order?
So you can, if I didn't put ordered here, usability would have to appear within 3 words, in a window of 3 words.
Before or after?
With software, before or after. Ordered is just an additional full text selection.
Just on the last bullet, where does, in the sub-expression for contains, where does books get bound? Is that, are we just continuing along from section?
Right, so here, no.
Slash books.
Where is it? So here, what it's really doing is returning sections that contain a keyword from any book, right? Because you're sort of like, right, but you could do a dot, right? If you want to have your book, or bind it to a variable and reuse it later. Okay?
If it was, if it's not books level, it is like at each node you're getting a query string out from the title under it. I mean, that query string appears like it is changing every time based on the context node.
So no, this is not changing, right? So this is being reevaluated from books, which is basically the root, right? But you could make it, change if you sort of, for example, you could use the dot being the book here, right? In fact, here the dot is not really the book. I mean, it's a bit more complex to write something where you want the dot to bind to whatever your latest context is for the XPath expression. But you can do it, right?
Dot is section, right?
Here, dot is section. Exactly, yeah. But if you wanted to return sections, you could sort of do this and do dot/section without having the section here, okay? And
Meaning if books is at the top level, you could put in a slash, and that's how you can define what context.
yeah, so
Right, it's fiction.
Yeah.
You're missing a
Yeah.
slash at
Yeah.
the
right. So for example, here I could have just put in section inside /ft contains, and then do a dot here, which would be the dot of my book.
I can't see the laser pointer, so
Yeah,
just do what you're looking at.
You're going to use the other laser if you're going to point with it. I know it's pain to have two, but that one.
Oh, yeah.
I
So
just-
the
this might
expression
not to
that-
kill anyone with this.
Yeah,
This is
it's not dangerous.
Okay, so
The last bullet, the expression after which contains actually returns a sequence.
yeah.
Is it all the? I understand it's being atomized for.
Yeah, tokenized, but no. But
And then the question is, presuming it's atomized, are all the words or ended?
okay, so there is a default in the system that you can choose, but FT word has other keywords that say all or any, so you can add them if you want to override the default here. Okay, so you can add any as a keyword, which would mean anyone, or all if you want them all to appear within this. But it's part of FT word, of the keywords within.
I didn't get that answer. So you're saying everything is getting concatenated there, or what is happening?
So here, if you don't specify anything, it just depends on the, let's say the default in the system is any. When it looks at something like this, it evaluates a string, actually a sequence of strings, and then it tokenizes them, so you have your sequence of strings. And if you're just using the default, it will use any. Okay? If you specify any, which is part of the FT word, it will, all or any, whatever, you can override the default. All right.
But on top of that, could you also have your same sentence or something? You can also use all of it.
Yeah, you can basically just, an FT selection, where is that? An FT selection composes with itself, right? So an FT selection can sort of just appear. So that's the idea, is sort of just you can compose them, and then show you how the semantics works for this.
One more question. So these semantics are equivalent to XQuery contains. It means that there is no synonym substitution or something like that.
So here, so far what I showed is this notion of FT selections, which is, you can think of it as being FT word or a combination of FT words in a certain way. For example, FT distance is subsetting the FT end, right, over FT word. Now, FT match options are like modifiers that actually some of them exist in the Verity system, not all of them, but modifiers that operate on words. Okay, so you can say things like, book title, FT contains usability, case sensitive with thesaurus synonyms. Right? So these are modifiers that are going to operate on individual keywords, and then we have like rules of how to push the modifiers around, and what's the context of a modifier. But these are just syntactic details. But really, the idea is that there are these FT selections and there are match options, and you can sort of all put them together. And then some interesting things, interactions are, for example, if you're doing a window between two keywords and you're saying with stop words, whether you're taking stop words into account or not, you count them within the window or not. Okay, so there are some interactions like these. You can say things like, this returns true or false, whether there is a book title containing utilisation language French with stemming. So you want like stemmed forms of utilisation in French, and this keyword with wildcards. Okay, this is doing what? Ors and oh yeah, there are special characters that are context modifiers that are going to be applied to web testing and software ordered. So here ordered is going to be applied to usability, web testing, and software. Okay, well, I mean any of these two and software. Okay, let me go into the semantics. I think it will be so the semantics is fun and interesting. It's very simple.
One quick question. In the previous slide it says language French. Is that off of the xlang attribute? How do you figure out the language that it's in?
Okay, so language is a modifier, which is the FT language option, which specifies which language you're going to interpret this keyword in.
Yeah, stemming rules change with language.
So the stemming, yeah.
Okay.
Stemming depends on the language that you have.
Query language. Yeah. It's a query language.
It's the language of the keyword, right? In which, yeah. All right. So here is how the semantics works. So there's this full match data model, which is basically just the set of keywords and positions within nodes. Okay? So if, for example, if you're doing, I'll show you an example, but if you're doing an FT word, right, here, usability, what happens is that the full match model gets instantiated into all the positions of usability within title, right? So these are all the matches or hits, right, possible hits. Okay, so just a few words and then I'll go into the example. So full match has a hierarchical structure that we represent as XML. So what we do is that the semantics of FT and the semantics of each FT selection, apart from FT word, which builds the initial full match, all the others are basically specified as transformations of input full matches into an output full match. Okay? As a result, we just specify the whole semantics in XQuery. Okay? It's just easier to specify it. So here's an example. Okay, so the example goes this way. Here is a piece of text, and just assume that every single keyword in the text is sort of numbered with an ID. Okay, the ID can be this, but it can be anything else. The only thing you want to make sure of is that the order is preserved because we have ordered FT selections. The proximity is sort of preserved in a certain way. You have to be able to answer proximity queries. It doesn't have to be contiguous. It's just that your proximity, function over positions has to sort of obey the semantics. And let's see how we can evaluate the query like this. We want to return. We will return true or false, depending on whether there is, if at least one book contains usability with stemming and rows, window at most 10. Okay, so there is an FT word here. There is a match option. There is an FT end, an FT word, and there is an FT window. Right. So really the plan, if we may call it a plan, it's not really a plan in the sense that it's not an algebraic plan that is optimized. It's just like an execution model. It starts like this. There are two FT words, usability and rows, that build the initial full matches for usability and rows within the books. And then there is an end between usability and rows, full matches, that itself returns a full match. And then there is a distance that sort of operates on the full match and filters out those that don't satisfy the window condition. So here is how it works. Initially, we have usability with stemming. We build the first full match, which is basically, it has just two answers, which are just two positions, 11 for usability and for users, which is a stem form of usability. And then another full match, which is rows, right? So there are two full matches built by the first FT words on usability with stemming and rows. So here's how the full match is built. It's actually an XQuery function, expression. What it says is that you start with an evaluation context, which is a set of elements over which the full match is being built. Then we have a search token, okay, with usability, users, and so on. Match options if we need to. And this is a query position which is used for order, to keep track of the order in which the keyword appears in the query, because we may need it for later. And it outputs a full match based on what? Based on going and getting all the positions of the search token within the evaluation context. Right? We get all the positions. We build one answer for each position. So that's what we got. We got this for usability with stemming and then this for rows. How is FT end specified? It's a Cartesian product. Okay? What it says is that really what FT end is, it's sort of looking for all answers that contain both solutions, one for usability and one for rows. Okay? So it takes two full matches, two instances of full matches, and build a new full match, okay? Which basically is just doing a Cartesian product between these two. So that's a result of an FT end. There are two solutions, two possible hits. Any node that contains any of these two is an answer, right? So it contains usability and rows, users and rows, okay, at these two positions. Okay, so that's how it operates. So you can see that it accepts full match instances and returns a full match. And then the window operates on this. It sort of just what it does, it goes in here and checks the window predicate, right? So it takes a full match, it's like a selection, and returns a full match, which satisfies the window. In this case, it was at most 10. Okay?
So your window also consider the tags?
The tag. Oh, yeah. So see, an implementation of such a language has to sort of have this semantics, right? When understanding full matches and returning full matches. But obviously, where is the back here? The initial tokenizer, right, and how you identify those words on which the search is going to happen, is sort of implementation defined. But yeah, in here I just tagged everything with an ID. Okay, so that's where the difference between two systems is going to show.
So I could actually search for the tags as well.
Yeah, yeah. Just if you treat them as keywords, if your tokenizer just treats them as keywords, it just numbers them. Okay, so just a few words about GalaTeX, and then I'll go into scoring. All right, so GalaTeX is our implementation of the XQuery Full-Text language. It's actually the first conformance implementation of W3C. It's really a conformance implementation. Just took the spec and implemented everything on top of Galax, the XQuery engine. There's a web demo. It includes W3C, XQuery Full-Text use cases, and you can put in your own queries. And you can, hopefully a week from today, you should be able to download the source and play with it. Okay. Here's how it works. The Galax query engine is here. All those functions I showed you, right, the FT word, FT window, and so on, they're all written in XQuery, right? And so we wrote those functions. They all operate on full match, okay? Which means initially we need the pre-processing of input documents to find, those individual positions of keywords and instantiate a full match model. And we store all this in inverted lists. And then we have, all the operations on positions are sort of defined on those inverted lists. Getting positions to build the initial full match, containment of positions from an element and a position, word distance, and so on, okay? And then we have a parser, obviously, that understands the end user syntax of full-text query and generates an equivalent XQuery, because it all boils down into calling those functions sort of to build full matches and return. And we return this, okay? So which means you can take pretty much any XQuery engine and just put it in here, right? Extend it with these functions, have this pre-processing that understands individual positions of keywords, and that's it. Okay, so this is how it looks like, just to give you an idea of what you may expect. So if I have a query like this that's looking for returning subject that contain usability testing, a simple query, it all translated into function calls, right, that operate on full matches. This is the one that sort of identifies nodes in a subject that satisfy or not the expression, and this all generates a full match. I mean, obviously, this is a very simple example, but this is, see, the default is any, right? So it tokenizes this into keywords. Default is any, and returns a full match. And then we take each node and sort of check it against the full match, whether it contains at least one match within the full match. Okay, so you can play with the examples that we have there.
I didn't quite understand the validate part.
Oh yeah, it's just because the which was here, right, somewhere here, right? Because we have an XML schema of full match, and everything that generated we validated against that XML schema. Okay, so yeah. So it's all sort of like a subsystem that's all based on this full match, which is defined within that XML as instances of that XML schema. Right? And we have functions that are written in XQuery that instantiate full matches and understand full matches and consume and produce full matches. Because it's like a subsystem that is within that XML schema that we basically instantiate here. Okay, now I get into the scoring. How much more time do I have?
If people need to leave early, that's fine, but we're scheduled to go to.
Yeah, I have
That's
one
great.
quick question. So in this approach, it seems that the full-text search itself, match itself, does not define a query context. So the context is defined by the path expression, and then you simply check whether within that string that you have formed, whether this condition is satisfied.
Right. When I build the first full matches, I build them based on my evaluation context, which corresponds to my elements over which the search is happening. And that context is identified by some XPath or XQuery that finds me the elements over which the search.
I understand that part. So you could not say in this that usability, whichever node usability occurs in, within its descendant or within its child, rows should occur or something.
Oh, I could. I mean, I just use XPath or XQuery for that, right? I mean, I could, let's take a simple example.
Between the two, you could not then define any distance.
Yeah.
Right?
All the full-text search primitives I have are within a node.
Right, and that's why it seems to me that the full-text search really does not define a context. The context is still defined by the path expression that you are using in your query.
Right.
Which means that we could also consider an alternative design where you simply had your relational full-text search that we know of, and then within this, you simply refer to the relational functions, full text function, do the evaluation, and since you remember the context, that would have been an alternative to what you had done, which would be more like SQL MM embedded within XQuery.
Right, so what you're saying is that it's your full text search that determines dynamically the context over which you're searching. If you know that your context statically before writing your query, you can express it here. So anything, if you know that what you're searching over, if you know where your search is going to happen, you can write it using XPath, right, or XQuery.
Like in your example, book content. So we know what the context is.
Right.
And then we do some full text search.
Right.
But if usability is found within content, let's say abstract,
right.
You are not switching the context to abstract to do further search on software.
So when I say look within whatever content, it's actually the whole subtree underneath it.
That's right.
Right.
But if within content there was an abstract
right.
where usability matched,
I'll find it within
yes.
that content.
But if I wanted to express that you don't change the context to abstract anymore once you do the match.
Well, my context is content, right, which itself contains abstract. So my context is a whole containing tree,
right.
subtree.
That's why it seems to me that I could have also done a very similar thing by saying, okay, I had this full text match with a SQL that I support, right. And I simply reuse it here. Maybe we can talk about
this. I think
yeah.
we'll have an opportunity to talk
Yeah, okay, great. Yeah. So one thing we cannot support here, for example, is dynamic context identification. For example, those methods that are based on, like, you're looking for those two keywords. That's all you're saying. I'm looking for these two keywords. Return whatever fragment contains those two keywords. Like what XRank and TeX and the systems do. They sort of use things like least common ancestor. And then they say these are meaningful, returnable fragments to the user. So those fragments sort of returned, decided based on the keywords, the data, and right. That's not. We don't have that here yet. Okay. Well, I mean, we could have something like what has been proposed by Jagadish and others about writing least common ancestor, basically, right? That could be one possibility, but we don't have it right now in the language.
It still can be written in XQuery.
It cannot be written as you cannot, because least common ancestor is not a primitive that you have syntax for at the level of the language. I mean, you can write, I think you may be able to write like some function within XQuery that does it for you. I'm not even sure you can, I don't know.
If ancestor access is supported, then I can intercept.
That's true, yeah. But then you would have to write a whole program or whatever, XQuery expression that does that. Yeah, I mean, at the level of the language, we don't have it as a primitive. So we don't understand how it sort of talks to the other primitives in the language and how it evaluates using full matches and so on. So, okay. Scoring, which is the most controversial part. All right, so scoring. Let's look at what we have right now in the XQuery full-text specification, and for which the main representative of, let's say, the world who's trying to do full-text search agree. What do we say about scoring? We say that, okay, so far what I showed you is just, a very Boolean interpretation of full-text queries, right? I mean, we have these matches, and then we take our nodes, and then each match, if a node contains one of the matches, it's an answer, otherwise it's just out of the loop. Okay, so what have we been doing about scoring? We have been saying that ranking answers, obviously, is very important. That score value should reflect the relevance of an answer to a full-text expression. I mean, it's important, but it's a general statement. We also said that score value depends on the scoring. Obviously, score values depend on the scoring algorithm that's used in the system. And as Mike Reese likes to put it, it's a secret sauce algorithm. But we have been trying sort of, come up with something, right, to understand how, the scored part of the language talks to the other parts of the language. I mean, we just want to say something about it. And even if different vendors distinguish themselves from each other with their scoring, the accuracy of their scoring algorithm, sort of want to try and push in a little bit more structure into this world. So the score is of type in the range 0, 1. Okay, so that's widely admitted, and people are happy with that. One of the reasons why this is there is because then it helps do some estimations, right? For later to do things like top K pruning and so on. The other thing is some form of monotonicity. Score values greater than 0. For score values greater than 0, higher score should imply higher relevance to the query, right? So it's the idea of sort of like the ranking, should reflect something about the relevance of answers, right? Something that ranked higher should sort of be more relevant to the query. And the thing that I want to dispute here is that what we have been saying is that if the Boolean evaluation of the full-text expression evaluates to false, then the score must be 0. Okay? And by saying this, we sort of ignore a whole 40 years of research in information retrieval. I mean, obviously, what people have been doing in information retrieval is saying, if the Boolean, evaluation of some expression, evaluates to false, then I may return. I mean, actually, no. In information retrieval, no answer is irrelevant. All answers are possible answers. They're all relevant, but of course, their degree of relevance changes, and and then you do ranking and return answers based on their degree of relevance. So what we have so far in the language is things like this. I mean, at the syntactic level, it's pretty powerful, given the limitation that we cannot extend the XQuery data model. So, for example, this is a query that returns. The first query is a query that returns scores. It uses the space of the flower expression, basically, to benefit from this, to sort of create this correlation or binding between an element and its score. Right? So what we're doing here is we know that within a single flower expression, actually the semantics, the formal semantics of a flower expression is expressed in tuples. Right? It just takes every variable and instantiates it in the scope of a for. Right? So here what we're saying is that for B in books, score $S as B content, FT contains, blah, 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 and so on. So I can score actually on anything. I should be able to score on FT contains. I should also be able to score on scalar predicates, and I should be able to score on whatever, this containment of author within book, right? And I magically return scores here, and then I return them for each book. The other thing that we can do is a bit more sophisticated. I don't quite like it because it's sort of anyway. So what this expression inside returns is a sequence of P, whatever sequence of items, and then because it's a sequence, it's sort of ordered, and it says that it needs to be ordered by score. And then what this expression does, it uses the position indexing in XQuery that says basically what I want to return is the 10 most relevant results. It says for each result in this sequence, return the 10 first ones that you encounter, and here they are. And this sequence is produced by sort of ranking books based on their relevance, this expression. Okay, so we can do to a certain extent, even if we don't have the ability to return tuples, we can sort of benefit from the or leverage the tuple space of flower to sort of return elements and their score. Okay. Okay. What I want to argue for is the following thing. I want to say that when a full-text expression is true, it should imply that score is greater than 0. Okay, so that makes sense, right? And which actually is also something we already have. When a score is equal to 0, then that should imply that the full-text expression is false. Okay, right? I mean, if we ever want scores to be equal to 0. And what it means is that the full-text expression, which is false, should not imply anything for score. Okay, I want to be able to sort of return those exact answers like we mean it in databases, and also some approximate answers. Okay. Right, so answer satisfying the query approximately may be returned.
Score less than 1.
Score less than 1.
Right.
Oh, yeah, well, of course. Yeah, given the fact that scores have to be between 0 and 1. And just one last thing. And as a result, I actually want to be able to say that I want to score on keywords, full text. FT contains expressions, whatever they are, and also scalar, like price and so on, and also structural query predicates, right? I mean, why not? Okay, yes?
So
that second requirement just seems to be equivalent to the first, right?
But really the most important one here is this one, right? That if a Boolean evaluation of the expression is false, that should not imply, that score has to be equal to 0 or anything. Okay, let me just walk through. So this is like jumping from 34 to 35 is like there's a wide gap, and I sort of I'm trying to make a point here, but I don't know if people are going to be convinced. But I mean, so in fact, what I'm going to try and present is just like how can you do scoring based on approximating structural queries. Okay? And how can you do it in a principled way by extending existing methods like TF-IDF, or sort of getting inspired by existing methods like TF-IDF. And then maybe later I'll sort of say that this also applies to content. Okay, but okay, let me go there. All right, so there actually have been just a few contributions on approximate XML queries on structure. Okay, what I want to show is how, what we did is I tried to study a bit more query approximation on structure in XML and define a family of scoring methods. And I'll show you why it is a family, actually, that there is no one way of matching the structural predicates. And there is actually a wider application to this. I mean, there's application to heterogeneous data sources. If you want to put data sources, do like, let's say, mapping between different data sources, you may want to do it in an approximate fashion, okay? And or at least understand queries approximately instead of having one exact schema. And also on XML querying on unreliable structure. Okay, let me go into my example. So I have let's say, an XML document or 3 XML documents, it doesn't matter. These are 3 fragments. And I want to match this query, okay, that's returning books such that in their info, they contain an author, it contains Dickens, and a title, it contains Great Expectations, and an edition that contains paperback. Okay, so here's how I represent my queries. Okay, so typical 3-pattern queries that people are familiar with. I want to return books that have an info child, which contains author, that itself contains Dickens, and a title child that itself contains Great Expectations, an edition that contains paperback. So obviously, if I look at this query, it matches exactly. This fragment matches this query exactly, while this one doesn't, right? Because it doesn't have edition. And then this one doesn't. It's even worse because edition appears under info instead of appearing. So there is this structural variation. And that's what I'm going to focus on, really. I mean, the content is something that I'm going to forget for the rest of the talk. So there are these variations, right, over the structural conditions in the query, and I want to somehow I want to be able to capture these as answers and be able to differentiate between these answers based on their scores. Okay, so obviously, if I do just a pure Boolean evaluation, I'll only be returning this, right? Okay, so in order to do that, we a while ago, actually, in the EDBT paper, we defined these 3-pattern relaxations as transformations. I mean. Conceptually, you can think of them as transformations on the initial query to sort of try and capture all variants, on structure. Okay, so for example, this leaf node deletion is something that makes a leaf node here optional in the query. It says even if you don't find an edition node under book, you can return book, okay, with a certain degree of relevance. Add generalization, what it does is that it says, well, here I'm asking for a parent-child relationship between book and edition. Well, if edition appears as a descendant of book, I may consider it as an answer, but I have to sort of capture that somewhere and be able to say that answers containing edition as a descendant of book have a lower score than those containing editions as a child of book. Okay? And this one is another kind of transformation that sort of says it's Subtree Promotion. What it says is that here we're having a very strict path between book and author, but what if author appears under something else or directly under book? Okay, so I sort of make this info optional. okay, in the path between book and author. Okay, so this may seem, very specific, like just a few transformations on a query that may capture some of the data and not all of it. But really, what we tried to do is sort of to come up with a framework to approximate XML queries on structure by defining atomic operations, okay, on the query that, if you think of them conceptually, would correspond to sort of rewriting the query in an exponential way into all variants of it that would match exactly the data set. All right. So in fact, let me tell you. So one of the what Schlieder did one of the related works is to have this rewriting-based approach, which obviously has its limitations. You don't want to sort of start and generate variants of the query. And what we did previously is to encode the query relaxation in a single join plan. So if you think of your query as a left deep join plan where conditions can be either parent, child, or ancestor descendant, then all the relaxations that I mentioned are actually can be encoded in a single join plan. Okay, so you don't have to do either multi-query optimization or. So basically, what's happening is that you're saying, what if I want to make addition optional? Well, that corresponds to turning this join into an outer join. Okay, so if I do an exact evaluation of a plan like this, the plan is incomplete, but it sort of has all sorts of structural predicates here. If I do an exact evaluation of a plan like this, what do I get? I get books that have an addition as a child, or whatever predicate I have here, an info as a child, and then a predicate between info and author, and predicate between info and title. But then if I want to relax it, I sort of add in, do some transformations. I say, if I want to make addition optional, I turn this into an outer join. If I want to make info optional, I turn this into an outer join. If I want to do subtree promotion, so earlier it was promoting, maybe addition was through info, or I don't quite remember. I say author was through info, where author, instead of just having a parent-child relationship between info and author, we have parent-child relationship or a descendant relationship with its grandparent. Okay, so we showed that each one of these transformations can actually be captured in a single join plan, and then what you can do is just basically apply top K processing here. Okay, so obviously the assumption is that you know what the score of matching each one of these is, or what it provides you with, and that's what I'm going to talk about. But if you assume that every single atomic part of the query provides you with a certain score, then there are some properties that you can guarantee that say that the more portions of the query and answer matches, the higher its score is going to be, and this kind of thing. So this is just to point into some piece of work that we did, and that actually also mentioned something that has, like a more recent piece of work is about saying you may not want to do a batch processing of these answers. You may want to do like adaptive processing and treat every tuple in a different way. But I guess this is just for reference. So for scoring functions, obviously, it doesn't matter, what kind of plan you have and how you're doing your evaluation. Scoring functions have to sort of satisfy certain conditions. So obviously, top K answer quality depends on the scoring function. How you're sort of scoring your query. Are you scoring it on a binary fashion based on each relationship, structure relationship, or in a different way? And really.
One feedback to that if you go back to your ordered and within a distance of 10, for example, then you have to order your tree in the appropriate way.
Yeah, so in fact here I'm cheating because I'm not really showing you how to score based on content. I'm really talking about structure, right? So I'm really talking about these things. I'm forgetting about these. I can mention this later, or you can talk about it more. But an efficient top K query processing requires scoring functions to be monotonic and fast to compute. Okay, so these are the two things that we need. And in fact, there has been very little attention given to scoring functions for structured and semi-structured data. All these works I mentioned earlier, the ones here, they really just say, there is one way of scoring data, and let's assume a certain decomposition of the query, and we'll show you rewriting algorithms of, that make that assumption and how you're returning answers based on scores. But not really, there hasn't been any, work on how do you do the initial scoring, basically, of your query components. And obviously, the TF-IDF has been extensively studied over text data, but there hasn't been much on scoring the structure. Okay, so what I'm going to describe is, scoring functions inspired by TF-IDF for XML. Okay, let's look at how TF-IDF really works. So on the left side of this table, we have in information retrieval. I mean, you're searching over a document collection. Your entities, or what you're returning, what you're searching over, are documents, right? You're searching over documents and returning documents. While here, we're searching over nodes, XML nodes, and returning XML nodes. Okay, so the scoring really happens needs to happen at a lower granularity. The query language usually in information retrieval is keywords, right? You have a bunch of keywords, and each one of them carries its own score, and the scores are being combined to sort of give the relevance of an answer, which is a document, to the set of keywords. Here, what we have is a tree pattern. Okay, I'm focusing on the structural part. What an IDF defines, an IDF is actually is a function of the fraction of documents that contain the keywords. Okay, so it's pre-computed, and it sort of just defines the importance of a given keyword over all the document collection. Here, what the IDF, in fact, the IDF should be a function of the fraction of return nodes, which are the nodes that we're dealing with, that match the query tree pattern. Okay, so in order to compute an IDF here, what we're taking into account is a document collection. Each document, we can compute IDF for it, and we're taking into account the fact that we're looking the query language, which is keywords, right? While here, we have set of nodes and query patterns. Okay. The TF, which is a term frequency, is a function of the number of times a keyword appears in a document, in a whole document. While here, the TF should be the number of ways the query tree pattern matches the return node. Okay, so it's the query here now is a whole pattern. It's not just a single keyword. Okay, so the properties should be for monotonicity. As I said earlier, scoring functions need to be monotonic, and they need to we have to be able to compute them quickly. I mean, efficient to compute. So for monotonicity, let's see how for structured queries this can be sort of obtained. So. Obviously, the monotonicity is satisfied by a few requirements, which are exact matches should be scored higher than relaxed matches. Okay, so if you remember, our query was this. Okay, and this is a data too. So the score of data that looks exactly like the query should be higher than something where pieces of the query, lack.
Sorry, what do you mean by monotonicity? Do you mean that larger documents will give you a larger score?
No. I mean that the higher. So one of the things with monotonicity is that you want the score in your plan to grow. So the more parts of the query you're matching, okay, in your query plan, the higher the score should be. Okay. So it's based just on how much of the query you're matching. Okay. So something that matches this only, and that doesn't match this, should have a lower score. So the other thing is that returned elements with several matches should be ranked higher than those with fewer matches because of the TF. For example, in a document world, a document that contains a larger number of that particular keyword would be scored higher than a document that contains a lower number in general. Okay, it depends on the scoring method, which is TF star IDF. Which is basically this, right? So if you have things like, addition appearing twice, then the score of B should be greater than the score of A. And however, the way TF-IDF is traditionally combined in information retrieval, which is TF star IDF, does not satisfy these requirements in this context. Okay, and so we came up with this thing that is IDF. Everything is scored by IDF, and then we break ties with TF. Okay, so let me show you how this works. Okay, so now how do you compute the IDFs? Okay, of answers. So the first way of doing it, which is the most expensive, but actually the most accurate, is to say that it's what we call tweak scoring, is to say that basically the IDF of this is based on the number of times, the number of books that satisfy info, which satisfies author, which satisfies title, which satisfies edition. So you have all the correlations here that come from structure all together, okay, in the IDF computation. Another way of scoring it is based on path scoring, right? That only looks at paths in the query, okay, and sums up the IDFs. But obviously, you're losing some of the correlations here. Another way is to do it on a binary basis, right? So basically saying that what matters is the relationship between nodes in the tree with the root. And that's exactly what is done in information retrieval. Basically just taking the root, which is a document, right, and the keyword, right? Here we have a bit more sophistication that comes from the structure, right? So that's what we examined. We looked at these three scoring methods, we compared them, and we sort of just ended up saying that path scoring is a good compromise. Okay, in most we tried the INEX data collection, and obviously it comes from the fact that you're not losing much correlations here, but in on other data sets you would, right? And what we did is okay, so this is like the idea of how do you sort of evaluate the IDFs. And, this guarantees some of the monotonicity properties we want, right? I mean, in this case, the more of these paths you sort of satisfy, the higher your score is going to be, okay? Well, I'm using sum. I could use any other aggregation function that also satisfies that.
Is it actually better for you to compute IDFs in such a complex way instead of maybe doing the simple IR global across all the text?
But you want the IDF to capture the relevance of an answer to the structure.
Well, generally, it's just how important the term is in the language.
Right. If you don't have structural conditions. Here I'm trying to make a case on, the fact that you want to capture these answers, right?
All I'm saying is it's not obvious. It's actually better the simple.
No, it's not. Yeah, and actually one of the things we're doing right now is a set of experiments on INEX and to see, how the user do the assessment. But yeah, I agree.
I have a question. So let's say I have a document and I have a text document and I run a traditional IR engine on it, and for a given query, set of my keywords, it gives me a certain score.
Right.
Then I take this document and I convert it into a very simple XML, which is just a root and the entire text as one node.
Yeah.
And I run the same query again.
Yeah.
Would I get a different score here?
No.
Because
Not here.
your number of matches is the TF is 1.
Yeah, because it's the keyword-based scoring here, right? You're not taking structure into account. Okay, just keep in mind the fact that I'm interested in returning fragments, so different fragments of my document would have a different relevance to my keywords, so I sort of have to take the structure into account. And my query might specify some structural conditions, and I want to sort of put in the query as a parameter in my scoring, right? It's part of the structural conditions in the query. The scoring is not only based on individual keywords, it's also based on the shape of the query, and that's what I also wanted to take into account.
Yeah, so what I was wondering was that there is a certain notion of score, because this keywords matches the entire data in that one node.
Right.
And the notion of structure here is not much because there is a single node.
Right.
And there is a certain notion of relevance or score because you are taking the structure into account.
Right.
So how do you put these two scores together?
Yeah, so we do have actually in this paper, we do have a discussion on how to put these two together. We have I started changing my mind from this approach that we had, but it's fine. Really the idea is that we just treat this Dickens author as another predicate over which we do our, okay, where is it? Here, our tree pattern, okay, has either predicates of parent-child, type parent-child, or containment, right? So it all, is in the same framework of this is as if you had this is as if you had an additional edge here, right, which correspond to an ancestor-descendant edge with keywords. So everything boils down to sort of putting together scores that are based on, or depending on how you view depending on the scoring method that you have. If I look at my query here, in fact, what happens here, which I'm ignoring, is that I would have additional plus book / paperback plus book / Great Expectations plus book / Dickens. So it would be again part of the query. It's like whether it's keyword containment or parent-child node structural containment, it's all treated in the same way. Right? And here, what it would correspond to is just book edition / paperback. Same thing here, book info author / Dickens. Right? So that's exactly that's really what it means here, instead of just having this notation.
Kind of related question probably. So INX has this notion of content-only queries, where you try to return whatever fragments from the XML collection that match best in terms of the keyword matches and also fit best in terms of granularity of the fragment. So for those kind of queries, I think you need different IDFs depending on what granularity you return. So how do you treat that with your approach?
Yeah, so here we don't really do it. In fact, what we would, like a direct application of our approach, would just say we have a binary scoring which corresponds to each node / keyword, and we compute the IDF or each node / keyword, right? And then we just apply it that way, actually. Which, in fact, the IDF, the way we're defining it here, doesn't take the all those discussions in INX which have to do with how large the size of the fragment. But I could sort of parameterize my IDF and add, a fragment size in it, or maybe my TF. But it really just boils down to binary scoring. That's the only one that would capture the content-only queries.
Actually, if you wanted to regularize it, you could take your database and score every node with a score based on the query. And then the further away the node is from the exact answer, it will be a smaller score.
Yeah, but that's just one way of doing it. That's a binary scoring that you would apply, for example, to content-only queries. But your binary scoring, but you may want other kinds of things. For example, you want to take more structure into account. You could say, the content-only query, I could, for Dickens, instead of just considering book / Dickens, not book, but element / Dickens as my basic IDFs, I could consider this whole thing with Dickens only. So the number of books that have info, that have author with Dickens, if this is my returnable fragment, okay? So in advance, I could sort of decide how the shape of my returnable fragment.
The part of your R, which basically says, don't tell me about nodes that don't match this.
Well, like XIRQL, for example, they do know in advance what are the fragments to return. Okay, so you could decide it. You could decide a certain fragmentation of your document and say these are the only returnable fragments, and this is these are over which I'm going to do my content-only queries. But if you want to be more general than that, you do just binary element / keyword. That would be your fragments, and then you compare those with each other. The question is how much structure you want to push into the IDF pre-computation. I have maybe 3 more slides, I think. Yeah, I know. So just as a quick, I definitely don't have time to go into the details of this, but just the idea is that, so I talked about a little bit monotonicity and efficiency, is that we sort of, obviously when you have an answer in the system at some point, a partial answer, you have to be able to identify what's the highest IDF, right, of that answer, how much of the query it has matched so far. And based on the query relaxations, we build this DAG, actually, where the highest IDF is obviously the one all the way up. Actually, this is the query, let's say. And the lowest IDF is this one, the one where I make all the other parts optional. Okay, and we have data structures that sort of, using hashing and everything, that given a partial answer, immediately in constant time identify what the IDF score of an answer is during query computation. But I could tell you more about this if you're interested. So what we have is these scoring methods that takes structural relaxations into account. The way content is perceived is really just as an additional predicate over which we can do our IDF pre-computation. We have these data structures that are the DAG structure and actually also a matrix to do top K processing. And we have this interesting adaptive evaluation of approximate answers. Just a few words on this, which is the idea is that people have looked at this adaptive query processing like the EDIES framework, where the plan might change during the query evaluation. And this is very much the case when you're doing scoring. Really, the idea is that if you're doing top K processing, you want the highest scores to be computed as quickly as possible so that you do your pruning, right, as early as possible in query evaluation. So in fact, the highest score for each answer could be obtained, at least those that, let's say answers can be grouped by IDF, right, the ones that have the same IDF, that are going finally to match the same yeah, so those answers might need to go through different join plans, right, to really maximize their scores, their intermediate scores. So the adaptivity is very much, really helpful here to sort of make answers, different answers, or batches of answers, go through different join plans for the same query. Okay, so we sort of explore this in this work. Okay, and these are just some open issues that we've been looking at. And so part of the answer about content only, or really the way we're doing this assessment for content only, is just to treat them as binary, with each element, right, as being a possible answer. Okay, but that might be very it might take too much time, right, to compute. Really, I mean, when you look at the query, it has two parts, right? It has what are the elements that really satisfy that query, and then what are the scores of those elements. And this has been usually like just all put together. And what we're trying to do is sort of to understand, to sort of say, okay, the space of all possible elements are going to be either all my elements in the database, at least the ones that contain my keywords directly or indirectly, or sort of try to subset those elements into other meaningful fragments in advance. And that only impacts the element identification, okay, what is going to be returned. And then we want to be able to plug in different scoring methods instead of sort of having everything into the same framework. Other things we're doing are, trying to come up with an algebra for scoring and understand there's some funny things happening here. The query equivalence is actually not doesn't always work. Like we worked on this query minimization in the past, which said a query that looks like this, there might be parts of it that subsume each other, structurally subsume each other, so it can be reduced into a smaller size query. Okay, but obviously, if you're doing scoring, the question is, can you preserve that equivalence in the ranking? Okay, so that's interesting. And that's it. I'm done.
Thanks very much.